Hello and welcome to the Oasis Developer Office Hours. So, do you hear me? Okay. Today we're going to get hands-on web development on Sapphire. So, Sapphire is a confidential chain running on the Oasis network. This will be a 60-minute workshop, and you are all invited to hack along me. So, if you have also any questions, please don't hesitate to pose it, and we will try to solve it together. My name is Matevz. I'm a software engineer at the Oasis. So I mainly work on the documentation and also various other tooling, like the Oasis CLI, the command line interface. So this CLI has also wallet capabilities, also allows you to manage your nodes, check the network status, check out the blocks. And I also work on other tooling, statistic tools, for example. I wrote a bunch of tests for the Oasis core, for the paradigms as well. Bunch of examples and other learning material. So yeah, today we're going to see how to start building with Sapphire. First, we will look at the Oasis architecture. Then I prepared 4 tasks for you. We will start with the confidential transaction and then signed view calls. We'll move to the front end, so how to connect to Sapphire with the browser. Then we will look at the precompiles. So Sapphire offers a number of useful tools for on-chain encryption, for example, random number generator and similar. So this is the precompile section. And finally, I will give you some ideas on how to proceed onwards after the workshop. So there are a number of interesting topics Sapphire can solve, and I hope I will get you some ideas that you would be interested in. So the programming knowledge is required, like basic JavaScript is okay. You are not required, to be a blockchain Solidity Ethereum expert. We'll also use the command line, and finally, you will need the Node.js environment on your computer and the PNPM package manager. Okay, now let's look at the Oasis architecture. So just a disclaimer: this is not a scientific illustration of the computing development for the past century. It's just a short summary of what I'm trying to teach you today. So before 90s, for example, in 80s, when the PC, the personal computer, first got widely available, this is a typical, persona. You have Alice and Bob, and they just bought a PC, a big box with a monitor, a keyboard, mouse, maybe not. And my point is that how they communicated with the computer, what their tasks were, they wrote something, some commands, they added some inputs to the computer. The computation happened inside that box, and the output was given either on the display or floppy drive or hard drive and so on. So the only way to communicate, to get data out of that computer is by using a floppy drive, or some kind of maybe a camera or something. There was no network at that time for the PCs. And then in 90s, then comes the web, right? So now suddenly the PC doesn't do the computation by itself. It just runs a web browser. And what Alice and Bob do, they fill some forms inside the HTML. They send the request to the server, and then on the server, the computation actually happens. The data is stored there and processed, and the response is generated, response is computed, and shown inside the web browser, right? And there can be multiple clients. So this is a typical, client-server architecture we even have today, of course. And there is a slight detail here. This handsome blonde guy is server administrator. And the reason why I put him here is, well, he has access to all the data. He has access to all the computation. Actually, when you are connecting to some server, you have no idea where your data is going to afterwards, and how the data is treated, computed, and so on. Right, and then comes the distributed ledger. So the distributed networks are much older than Bitcoin, but for the purposes of this workshop, I'll just focus on Bitcoin for now. So in Bitcoin, you have a number of nodes running in a distributed network. So each node is both a server and a client at the same time. And why Bitcoin is special in this regard is Bitcoin transactions are all stored in one huge public ledger, and each node has a copy of that ledger on his hard drive or something. And the way how to put transactions onto that ledger is you need to have some kind of a consensus which transaction will go in and which will not go out, or not go on ledger. And how consensus specifically on Bitcoin is achieved is that they decided to have this difficulty, and the first node that comes up with the number of leading zeros corresponding to the hash of the proposed block will have the permission to add the block to the ledger. Okay. Then the Ethereum comes along, and it wasn't that different in this regard. So also the Ethereum has this public world try. Everyone sees everything, and each node, if it wants to be in this computer validator set now, this proof of stake, needs to have a complete view of the world, right? So here we don't have a client-server architecture. We have this peer-to-peer communication and transactions among the nodes. And the computation is performed on each node. But in practice, if you're using a mobile phone and you want to use Bitcoin or Ethereum for that matter, you will probably not run a full node, right? You will have something called light client. And there is some intermediary between, it's called the Web3 gateway. So the way how you communicate with the network is it behaves like a typical client-server architecture. You connect with your web browser, for example, to this Web3 gateway, and the Web3 gateway then transforms the Web2 transactions into the Web3 world transactions. Now, from the trust point of view, that kind of sucks, right? I mean, you need to trust. If you run your node by yourself, then you can at least trust the hardware, and you can at least trust the software if you look at the source code. If you are connecting to some Web3 gateway out there, then again, you need to trust the Web3 gateway administrator that it doesn't leak your data. But anyway, as I mentioned, Ethereum and Bitcoin ledgers are public, and everyone can see everything, every smart contract, every transaction. Okay, now let's look a bit how the Ethereum network stores data. So I already mentioned that you have this world state, and this world state is basically a huge tree, computer science data structure tree, and it comprises of 32 bytes long keys with 32 bytes long values. And basically every transaction, every data you want to store, every variable in your smart contract you want to store is like this. So it has an address, which is derived from the contract address and the location inside the smart contract, and the value, which is hard coded to 32 bytes. If you want to store a bigger value, then you need to concatenate consecutive number of nodes and then combine it to get the complete value. But we can extract, as I mentioned, because all the data is public, we can essentially extract complete storage of every contract out there. So now the question, $1 million question is, wouldn't it be nice if we could encrypt data and then you could actually do some computation which is well, private in that regard? You don't want to have your financial transactions available to everyone out there, but in the early 90s or 80s, when the PC was at your desk, no one could access the data if you didn't broke into your house or something. So if we encrypt data, sure. I mean, you have a smart contract and let the smart contract encrypt data, and now the data is stored encrypted on chain. That works, right? But the question is, you encrypt your data with which key? Because the only space the smart contract sees is the one on the blockchain. And if you store the private key, the secret key on chain, then everyone will see the key and will be able to decrypt data, right? Okay, so let's just brainstorm a bit more. If we are able to encrypt data on chain, then you would suddenly have a perfect distributed finance world where the order book wouldn't be publicly available. Suddenly you would get rid of all the MEV, the minor extractable value, because no one would actually know if the transactions were encrypted, then what your transaction is, and if you should change the order. If you're a miner or validator, if you should change the order of the transaction, because the transaction would be encrypted, right? And finally, you could have your personal data on chain, and it would be encrypted, but you would allow some contracts to maybe process them, and you would see the source code of that contract, and you would exactly know how the data is processed and if there's some leakage anywhere. And yeah, this opens like a huge opportunity. Right, so this brings me to this point. I mean, if you have a distributed environment and you know that each node needs to be self-sufficient in order to compute, then they need to have some kind of a way to do the computation, but not having ability to view all the data or something. And well, the magic word here is the trusted execution environment. The trusted execution environment is a hardware provided execution environment. And in practice, for example, if you take the Intel calls this, the marketing name for this is Safeguard Extension, the SGX. How it works is that it encrypts a portion of the memory, and even the CPU communicates with your memory through the encrypted channel. So if you have a node operator or a server administrator for that matter, and it would try to, take the oscilloscope and monitor the communication on a physical layer from the CPU to the memory, he couldn't extract any information because the communication is encrypted and the memory is encrypted. And this is perfect because you can run your application inside the some Docker image, some virtualization solution, and still, if it has this trusted execution environment support, then even if it runs inside the virtual machine, you cannot extract any information out from it. Okay, so the idea is, could we build a distributed network which runs inside the trusted, where each node runs a trusted execution environment, and inside the trusted execution environment runs the compute node, the compute software for our network. Okay, so ideally we should have the private computation. We should have the randomness. Randomness is important because the governance, for example, depends on randomness. The on-chain key generation depends on randomness. We should have private storage, of course. As I mentioned, we want to store data on-chain, but the data should not be visible. And we want to have end-to-end encryption, because when you communicate with the network, the HTTPS is not enough. You need to have the end-to-end encrypted transaction, because the transaction will get stored on the public ledger. So the transaction needs to be encrypted, and on top of that, you can add the HTTPS channel to your node, right? Okay, so if we take this, if we take the figure from before, now we have this web browser which access the confidential dApp in our case, and the network, the distributed network from the hardware point of view looks pretty same, but the Web3 gateway needs to have some extended calls to retrieve some confidential primitives. And now we basically have the same HTTP request as before, but now it's wrapped because we have the end-to-end encryption, the peer-to-peer encryption enabled. And between the nodes, you can also communicate with this end-to-end encryption. And the most important part, the computation now happens on each node as it did before, but it happens inside the trusted execution environment. So in other words, when you run a smart contract, when you do the smart contract transaction or a call, that computation is performed inside this trusted execution environment, and the node operator has no way to extract any information of what the smart contract is operated on which data it operates on. Okay, and this leads me to the Sapphire confidential EVM. So Sapphire is basically the whole introduction I made results in Sapphire. So we took the Ethereum virtual machine with Solidity language, if you want, and any smart contract out there, running on Sapphire is executed inside the trusted execution environment. The storage is encrypted, so the whole world trie is there. It can be publicly, accessible, but data on that world trie, inside the world trie, is encrypted. And for compatibility with existing Ethereum smart contracts, we also support the original Ethereum unencrypted transactions. So this doesn't mean that the computation itself will be unsafe. It just means that this end-to-end encryption is optional. I talked earlier. So the storage, the computation is still confidential, but just the transaction that is stored on the ledger is publicly visible if you do not decide to encrypt it. For example, there are occasions where you deliberately want to, show the transactions, the transaction you transmitted. For example, if you want to verify the contract, the deployment transaction, for example, the contract trade transaction should be publicly available to anyone, right? They should not. They should be able to see the bytecode you stored on chain. Okay, and just another figure, just to get you the idea of how the contract is executed, or how the contracts execute code on Sapphire. So suppose this on the left side is a Sapphire running inside the TEE, the Trusted Execution Environment. Another component here is the key manager. And the key manager is another runtime running in parallel on a subset of compute nodes. And when, for example, when you sign a transaction and that transaction needs to access to the confidential storage, it asks each time the key manager for a key to access the confidential storage. And the key manager then accesses the key value database to obtain the key for that specific contract and returns the key back to the Sapphire environment. And the Sapphire then processes the transaction, reads, writes back to the storage, computes the new IO routes for the block proposers and so on, and also returns to you as a user the result of your computation of your request. Emits any events and so on. So the point here is that even though Sapphire runs inside the trusted execution environment, it does not store any keys. So if Sapphire gets hacked, that's okay. The real danger is, for example, if the key manager nodes would get hacked, because this is where the actual keys are stored. And for Sapphire, they just temporarily get the key, do the computation, and throws away the key. How do we know that they throw away the key? Well, because you could look at the source code, and that exactly source code is running inside the trusted execution environment. That's what the whole attestation steps are there to assure you that the code that is running inside the trusted execution environment is really the code that you expect it to run. And just a slightly bigger picture here. So I just talked about Sapphire, but Sapphire is just one of the chains running on a complete Oasis network. So the network above is called the consensus layer, and the consensus layer is basically the governance layer. For example, if there's a network upgrade, as it happened 2 months ago with this Eden upgrade, this happened on the consensus layer. If there is the upgrade of a specific runtime, paratime running below on a subchain, then this upgrade is announced on the consensus layer, and it says like exactly at which epoch the version of a specific paratime will change, for example. So if also the storage is distributed in that regard, each paratime has its own storage. So if you just want to run a Sapphire node, that's okay. You can just run Sapphire. You can also run an Emerald node or Cypher node. There are some other paratimes here. For example, Emerald was our first paratime, which was EVM compatible, but it doesn't support encryption. It's not confidential. And the Cypher here supports confidentiality. The storage is encrypted, but it's not EVM compatible. It uses its own WASM WebAssembly language, and the smart contracts are written in Rust. We also provide the Rust SDK for this matter, but just to get you a bigger picture. And just a note: if you have some tokens, you will. I mean, the tokens are separated. You can have tokens on the consensus layer, and then you can move tokens from the consensus layer to paratime, and then from paratime back to consensus layer. So you cannot directly use tokens from one layer to another layer if there is no bridge or something else involved. And the consensus layer, by the way, the consensus layer does not support any smart contracts whatsoever. So this is on purpose. We don't want to Turing complete language contract support on a consensus layer because it's just too risky. Okay, so for anyone eager out there, and if anyone already knows how to write smart contracts on Ethereum, they can just bootstrap and jumpstart ahead and connect to the testnet Sapphire, for example, and try to deploy some contracts there using the original Ethereum tooling, and you're good to go. So the testnet.sapphire.oasisdev is the endpoint. Oops. And our block explorer lives on explore.oasis.io. Right. Okay, so now I will get started with the practical part. Maybe if there are any questions, let's pause for a minute here, and then we'll move further. The slides. Sorry for that. Okay, so there were some questions. So regarding the slides, I would kindly ask Neely if she could maybe share it view-only access from the Google Drive we have with everyone, or maybe export it to PDF and upload the PDF to our drive and share it. Sorry, I forgot. And there are some questions regarding the Sapphire downtime. So as I mentioned earlier, the architecture is something like this. And the main issue was inside the Web3 gateway because it didn't load balance well with the underlying nodes it connected to. So if you ran your own Sapphire node with your own Web3 gateway, then there were no issues whatsoever. There was an issue just with our Web3 gateway, and there were some nodes experiencing it's called the table compaction inside the Comet BFT, the consensus library we use. And the disks were a bit too slow, and where that compaction happened, the node basically froze for a few seconds up to maybe half a minute. And if the load balancer just picked the wrong node at that time, you would get random downtimes and some weird behaviors. And unfortunately, on the client side, the MetaMask is stupid enough not to retransmit the transaction if there's a timeout or something. It just waits for 5 minutes and then crashes. So it doesn't try to rebroadcast the same transaction if something happens in between. So the issues, how we fix those is, just simply, we added more nodes, basically. And the Web3 gateway had some weird non-random load balancer bug, and this should be much better now. But as I mentioned earlier, if you're serious, you should never depend on some public centralized services inside the distributed network. Each developer should run its own client node, for that matter. If you're a company, then you should run your own node, or maybe rent a node with the Web3 gateway. It doesn't need to be a validator node. It doesn't need to be a compute node, just a client node, so that you can rest assured to be sure that the transactions are transmitted. There is no censorship involved. That if there is a congestion on public blockchain or on public gateways, that you can use your private gateway for transmitting transaction, because the network was there, the network was intact, it was working fine, the computation happened, the blocks were produced, everything was fine. It was just this wall, this endpoints, which gives you access to the network, which were down, congested. Okay, let's go. So task number 1, confidential transaction. I prepared the demo starter repository, and it contains, let's look at it. So go to github.com/Oasis protocol/demo starter. Okay, so this is a monorepo. We have two packages. One is the backend, one is the frontend. The backend is there with the contract itself and tools to deploy the contract. We will use Hardhat. For those not familiar, Hardhat is a smart contract management tool. It's written in TypeScript, in JavaScript, put it this way. And you can use Hardhat to deploy your contract, to run tests, for example, to combine the private key of your accounts used for testing, for example, and then that private key, that account will be then used in actual tests, or to deploy your smart contract and similar. The front-end part, we'll look a little later, is the browser part to access your dApp. So let's go ahead and let's clone this repository. There's a code button here. Just go ahead and copy it. And I will use my command line git clone and this repository. Okay. So let's look at the contracts. Okay, there is one contract called the message box, and the extension is sol, which means the Solidity language. And this message box contract looks like this. So there's a public message stored inside the contract and the author of this message. And the only function is, well, the message you want to store and the message variable inside the on-chain will now contain your message, and the author field on the chain will store the sender of this message. So when you submit a transaction, you also provide the public key of the transaction and sign it with your key. That's the way actually how the distributed network knows which fees to take from and who is the sender of the transaction. And this message.sender is just a syntactic Solidity sugar, which gives you access to the address of the sender. So the address is derived from the public key who signed the transaction. Right. Okay. So this is the contract we are going to use. We are going to deploy and play with. And the next one, let's see. Okay, we will need. You don't see the slides, do you? Okay. We will need MetaMask for that matter. Okay, so I suggest you open your browser, and if you haven't yet, you go ahead and install the MetaMask extension. So head to metamask.io. Let's download it. Head to Chrome. Okay. Let's create a new wallet. You will need to come up with a password. And let's not do any backups for now. Okay. Cool. Next. Awesome. Okay, let's pin. So we'll have a nice button here at the top. So this is our MetaMask. And you can see that it also generated one account for us. Okay, got it. Yeah. So this is the address of our account. 0x denominates that it will be a hex value. 5v700 is the actual address. So if you go to here, you can see the full address of our account. And this is not related to Ethereum. MetaMask says it's connected to Ethereum mainnet, but basically the account corresponds to a key pair which is stored inside your MetaMask extension inside your browser. So you can simply, switch the networks, and you will have the same key pairs, the same account, regardless of which network you use. But still, we will need, to add the Sapphire testnet, because we'll be using that to deploy our contract. So let's go ahead and add it. So one way is to add it manually, but I'm lazy, so I will head over to our documentation, where we already prepared a magic button you just click on, and then the network is added. So head to create depth to Sapphire, and then you have this magic buttons here. You just add. So we'll use testnet for now, and I will add it. So this is the chain ID, the currency symbol. Okay. Right. So now we are connected, hopefully, to the Oasis Sapphire testnet. All right. And our balance, well, is still 0. So first, we will want to get some tokens. Originally, I mean, you buy it on mainnet. We use the proper Rose token, and you buy it for whichever amount of dollars you have. But here, because it's a test network, and the tested network can get wiped anytime, so I really suggest that you don't deploy any production services, production dApps to the testnet, because it may magically don't stop working. So yeah, let's go ahead and let's use our faucet, which deposits some test tokens to our testnet account. And this faucet is accessible on faucet.testnet.oasis.dev. So faucet.testnet.oasis.dev. Okay, and then as I mentioned earlier in the architecture slides, so you can get your test tokens on the consensus layer on top, but you can also get it directly deposited inside your paradigm of choice. So we will use Sapphire for this matter, and we'll just paste the address of our MetaMask wallet here. And I'm not a robot, I hope so. So the car, where's the car? Here? Is this a car? I suppose. Okay, no. This one or this one? I don't know. Okay, I'm not a robot. Awesome. Cool. So it seems that the funding request was submitted, and I should see tokens landing in a moment now to our account. I hope I typed in the address correctly. Oh, there they are. Cool. All right. Next step. All right. So now we have test tokens. Now we have our account. We will deploy our contract to Sapphire testnet. So let's go line by line. First, we need to go to our backend folder and type in the pnpm install command, which downloads all the dependencies from the network, from the internet. And then we will run pnpm build. This build step will compile our Solidity smart contract written in the Solidity language to the bytecode. The bytecode will then be executed by the Ethereum virtual machine inside the Sapphire. And it will also produce some other things like the ABI, the application binary interface. This is like a list of all the functions your dApp, your browser can access and call. So stuff like this, yeah. Let's go. So I'm already in the backend folder. This is okay. And let's see npm install. This will download all the dependencies. Cool. And then I have npm build. Okay, pm build, oops, build. Okay, it seems it works. So if we look at what happened, inside the contracts folder, we have our Solidity contract, and then this ABIs folder was generated, which contains this binary interface. Maybe we just look at it. So we can see that this set message, for example, function is here. It doesn't return anything. It accepts one string, for example. So this is something your deb compilers then take and produce a nice interface in TypeScript that you just type in like my message box dot set message something, and all the magic then happens behind the scenes. The transaction gets generated, it gets broadcast, it's waited then for a while, and so on. Right, and inside the artifacts, we have also, this one. We also have data for contract verification. So if you want to deploy a contract and you want to verify it, then this is the file you need to upload to, for example, to Sourcify service or Etherscan and so on. Oh, okay. Sapphire is not currently on Etherscan, but supposedly for any contract verification services out there, this artifacts contracts folder is the place where you want to look for this verification material. Right, okay, so the contract is now compiled. Let's deploy it. So the deployment instructions are here. So there's an environmental variable called the private key, where we will need to put the private key of our account. So our account in MetaMask, we will need to export that. And then the command is npx hardhat deploy. And on which network? Well, on Sapphire testnet. Okay, let's see. So let's open our MetaMask and let's export the private key. Account details, show private key. Okay. Okay. Right, this is our private key, 687E71 something. Okay. So let's try it out. Private key equals 0x and our hex value of the private key. And then the npx hardhat deploy, which network? Well, Sapphire testnet. Godspeed. Okay. And hopefully this works. Great. So this is the address, 595cc. This is the address where our contract was deployed to. And now if you want to communicate with our contract, this is the address where we need to provide each time. And yeah, we can now launch our Explorer and see if this is really the case. So if we go to explorer.oasis.io and type in the address, it says that there are no results found on mainnet, which is expected, but there is one result on other networks. Oh, really? Okay. And it's on testnet. Oh, that's nice. And if you click on the address, you get some nice info, like who created the contract, the 5v70 account. So is this really our account? 0x5v0, yeah. And what else? So there is one transaction related to this contract, the contract creation transaction, obviously. It does not store any tokens, any NFTs. There are no token transfers yet, no events. Okay. And this transaction which created the contract is here. It's in plain format. It's not encrypted. See this gray padlock here. And yeah, from2 is shown here. and the amount, the fee, which we needed to pay for the contract creation, the amount of gas we used. Okay. Cool. Now, what's with this format plain? Well, this is Oasis Sapphire specific. This is not anywhere inside Ethereum. It is the end-to-end encryption I talked previously. So the contract creation transaction in our case was not encrypted. But now let's look how encrypted transactions, would look like. Because the end-to-end encryption is something special in that regard. You need to have a part of the key on your side. You have the other part of the key on the other side, and when you combine the keys together, you get the shared secret used to encrypt or decrypt the transaction. And the interesting thing is that neither two pairs, the secret key will never travel across the network, so no man-in-the-middle attacks will be possible. So how is this achieved? Well, on the client side, for example, in our command line interface or inside the MetaMask, you generate a key pair. And then you request from the Web3 gateway the paratime public key, which you will use. So this is the other part of the key, which you will use to encrypt the transaction. And this is important because if you are connected to a malicious Web3 gateway, it can inject you with some, not the paratime public key, and you would encrypt it, in a good sense that this is confidential, but the Web3 gateway could, exploit this and steal your data. So this is why you should always run your own node and your own Web3 gateway. Right. Okay. So you encrypt and submit the transaction to your Web3 gateway, and the gateway relays that transaction to the compute node, and then the compute node requests the private key from the key manager, combines it with the public key, with your public key you generated yourself, and then it derives the shared secret used to decrypt your transaction. And then the computation is performed, the result is computed, and the encrypted result is returned back to you through the same channel. And then you use your secret part of your client key pair to decrypt the result. And now you would say, okay, this sounds pretty complicated, but actually it's not that difficult. The only thing from the developer point of view you need to do is you import our Sapphire hard hat npm package, and it automatically, when you import it, it automatically wraps the Ethers library, and whichever call you do afterwards, it will be encrypted and signed, right? So this is specifically for hard hat. If you are developing a front-end app, then you won't use hard hat there. You would use the standard EIP 1193-ish connector, and you will use this wrap function we provide, and put your provider there. Usually this is MetaMask or Brave or something, and it will get wrapped, and any communication afterwards will be automatically encrypted. Okay, so now let's see how setting the message and retrieving the message works. Okay, so this is already part of the demo project. I will just demonstrate it, how the code looks like, and then we will run the command to set the message and retrieve the message. Okay, so this is the hardhat config file actually, but something hardhat offers, and it's pretty nice to use, are so-called tasks. So one task we already used is the deploy task, and it's defined here. So what it does is it compiled the contract, it connected to the Sapphire testnet in our case, because this is what we passed in the -- network parameter. It got the message box TypeScript bindings and called the deploy function on that smart contract object, and it used our unwrapped provider. The UW in this case is unwrapped provider. This means this is the original, plain text provider. It's not using encryption. And then when the message box was deployed, it just waited a few moments and showed the address. Okay, now let's say we want to set message. This is this task here. So this message, this task will expect the address, and this is the contract address we are connecting to, and the message content. It will compile the contract. It will obtain the existing contract, so it will not deploy the contract, but just connect to an existing contract, and it will call this set message transaction. But in this case, we will use this get contract at. We will not inject any special providers as we did here. We will just use the original wrapped provider as it is, and this set message transaction here should be encrypted. And then we just wait for the transaction to finish and show the transaction hash. Okay, let's try it out. So previously we used this private key equals something and npx hardhat deploy. Now we will use set message, and then we will need to provide the contract address, this one. And the message itself, I would say like hello world from the Sapphire 101 workshop. Why not? Okay. And now hopefully the transaction will pass. And if everything works fine, it should also pop up on the Explorer side. Okay, the transaction seemed to pass. Oh, here it is. Look. So this transaction went through, and it's a contract call kind of the transaction, and it's encrypted. The format is encrypted. And if you look at the data itself, well, if you take the ordinary Ethereum transaction, you should see something which is decodable inside the ASCII hello world from the Sapphire workshop, and here it's encrypted using the ephemeral key I mentioned before. Okay, let's move on. So can I retrieve the message? Well, there is this function called message. Will it work? Okay, awesome. So this is the stored message, hello world from the Sapphire 101, and the author is ourselves. Okay, so we just transmitted an encrypted transaction. Congratulations. Now the question is, how private is this? And if you watch closely in the Explorer, there's the from and to field, which cannot be encrypted because the smart contract, the compute node needs to know which smart contract it needs to communicate with. You cannot hide that. The gas price, the gas used is also an important data because you will get your gas refunded, and it's pretty obvious how much gas the contract call will use. And for this reason, this is an important attack vector. We also provide the gas padding calls inside the Sapphire precompiles, so you can just pad gas upfront to a specific amount, and then from the external observer view, they cannot know which contract call did you exactly call, because it's just the address of the contract, but not inside the contract what did you call, because the gas is used for any contract call out there, for example, if you program it this way. And of course, the payload is also known, the size of the contract call. So if you have one function which has like 10 parameters and the other function which has no parameters, then of course the payload of the first transaction will be much bigger, and you cannot find it basically. You then need to prepare that each function will have the same signature in that regard. Right. So now we just learned that there are confidential and non-confidential transactions. And the task for us is, can we use the unencrypted transaction to set the message as well? Because as I mentioned earlier, there are cases where you want to publicly announce that there is some transaction out there which you transmitted, and everyone should be able to see it and decode it. And the answer is yes, you can do that. And basically, we'll just take the code from the deploy task here. So if we do this and paste it here. Okay. It will use the unencrypted version. Let's try it out. Unwrapped wider. Where's the unwrapped wider? Oh, here it is. Sorry for that. Where is this? Okay. Here we go. So there seems to be another transaction, and this transaction should be plain. Well, here it is. So welcome. This is smart privacy, and now you can decode this transaction, and it should clearly say that well, hello world from Sapphire. It's obvious here that this is a human readable string. It's not some random binary blob. All right. So we're a bit short on time, so I'll just move forward. Task 2, the signed view calls. So this is important. You saw earlier in our code that contracts here, we store the author and we take this message sender. There are two kinds of how you communicate with smart contracts. One are the smart contract transactions. Those are stored on public ledger, and for those you also need to pay some gas fee in order for them to be computed and processed. But then there's another way. The view calls. It's only a read-only call. You can call a smart contract. It's a read-only call. It happens locally inside the compute node. It doesn't write anything. It just reads and then immediately gives you the result back. And this is special because you can also encrypt view calls, of course, because you don't want to have the node operator access to your call data and the response. And what Oasis Sapphire is special in this regard is that this message sender object will always correspond to the one who initiated the contract view call. For this reason, the contract views need to be signed. And if it's unsigned, the Oasis Sapphire will just set this message sender field to 0. It will nullify it. Yeah. How does Ethereum do it? Well, in Ethereum, you can set the message sender by design to any value you want. So you can impersonate someone else and call view calls in someone else's name. And this is something we want to prevent, right? To summarize, basically, you can rest assured that the message sender will always equal to the caller, or if if it's a transaction, then the transaction is signed anyway, and it also matches the caller in Ethereum. But if it's a view call, then in Sapphire you can rest assured that this is the one who is calling, because the view call is signed, and if the view call is not signed, it wanted to impersonate someone else, then the message sender will be 0, regardless of which value the caller set this value to. And if it's an internal transaction call, internal smart contract call, then the message sender equals the caller of the function. This is the same as in Ethereum, right? So if you have a contract that calls someone else's function, then the message sender will be the one from the original contract who initiated the call, and not the one who broadcasted the transaction, us. Okay, so the task is this one. Let's force the message that it returns the message only if the one who requests it is the author of the message. So this is pretty straightforward, but one thing we need to do is that the message will now be private. So something like this. So if message sender does not equal the author of the message, then we will, panic. We will revert and say something like, I don't know, not allowed. Otherwise, we return the message. So this return will be reachable when the one who asks for the message is the author. Okay? This should be it. And now let's see in our hardcat. I think we already used the signed version. Yeah, this is the signed version because we just used the original signer here. So if we just try to deploy this, oops. Message. Okay. Well, awesome. So this new contract is now deployed. Let's write a message. Set message. Okay. But we need to use the new address. The new address is this one. So this is now a confidential hello world, put it this way. Hello world. Okay. Awesome. And then if we want to receive the message, it should work. And this message call will be signed using this key. So the smart contract will know that our author matches the private key we signed the transaction with. And this is the content, confidential hello world. But if we use the unwrapped transaction, so the original Ethereum transaction, which is not signed, let's use the code here. Yeah, we get this not allowed exception. Okay, so this is a proof that if we executed the view calls which are not signed, that the message sender will be nullified, and this condition here then fails. Okay, so this is a nice way, to do the access control and also to avoid this gas costs attack usually. So if the first thing you do is check that the query was sent by the allowed author, then anyone, without the permission can do whatever they want, but they will never be able to extract more information of how your contract behaves, what's the data stored inside the contract, and so on. Okay. Cool. Now let's look at the front end. So the front end is usually a more trickier because you need to integrate the MetaMask or whichever component to our existing code base. How it works is that it takes data from the backend. So we need to run this pnpm build inside the backend first. Sorry, let's run it. I forgot, do we have the confidential queries now? Maybe we should. Let me just remove the confidentiality part here. So we want. Yeah, this is fine. pnpm build. And let's deploy it. Deploy, where is it? Deploy, okay. And then what we will do is we will, so the front end lives in this front end folder, and we will need to store our chain ID, the contract address, and so on. The front end will connect to inside these .env files. So .env files are typical for the Node.js developers, and you have different flavors of them. One is for development, the other one is for production. So we'll just use the development, and we'll put the message box address here. The Web3 gateway can remain the testnet, and the network is also the testnet one. Okay. So hopefully now, if I do this, I'm not sure if it's okay. So if I just run the pnpm dev, I could connect to this localhost 5173 address. All right. And then hopefully it will allow me to connect my wallet. So what happens? Yeah, okay. Looks like something's borked. It seems some permission issue. That's weird. I can just build the front end. So this, if you run the pnpm dev, it uses Vite. This is a special tool which runs, preview of the front end, and whichever source file you change, it immediately reflects any change. And the same Vite is then also used for production builds. But yeah, maybe this is the issue. Let me just go to my local host now because I connected it to my dist folder. Oops. Starter Frontend dist to localhost. Okay. No, it's the same issue. Yeah, so this is the curse of the live streams. I would need to work on it, but basically the idea is that you can write the message here. The MetaMask pops up, and you can just send the transaction, and it also offers the encryption and signed view calls the same way it did from the command line. Yeah, sorry for that. But you can, I mean, yeah, probably just my machine. If you checked it out and try it locally, it probably will work for you. Or maybe I can just try a different browser. If it's Chrome specifics. Yeah, it works on Firefox. Don't know why. Yeah, it's okay. So let's see. Test, I suppose. But I need to connect to the right network. This one. Not sure. Or I can just use Dave. It should have some test tokens. Yeah. Okay. Set message. Okay, confirm. I think it's the wrong nonce. Yeah, sorry for that. So this seems to be buggy, but yeah, it should be working. Right. Okay, so let's skip to our last task. This is about the precompiles. So the precompiles inside the Solidity is a standardized language. You have, usual calls, arithmetics, control sentences, statements, and so on, functions. But then you also have some, extended functionality. For example, in Ethereum, you have this SHA-256 hashing, which is built in the Solidity language. You have the elliptic curve verifications and so on. What Sapphire does is we have some additional precompiles available. I mentioned the guess padding because you want to avoid guess attacks for this matter. Then we have the randomized, the random number generator, which generates random numbers or secret keys for that matter on chain. This is because we support the confidentiality. And we can also do some symmetric encryption like the X25519 or the Deoxys envelope decryption and so on. So for a full list, visit our docs. Again, there's a nice list of precompiles there. And how to use it? Well, it's already the npm package offers the Solidity contract precompiles. You import it, and then you can use it in your Solidity. Okay, so let's see it. If I go to backend, I do pm install -d Oasis protocol /Sapphire contracts. Okay, and then inside the contract, I do import protocol Sapphire contracts. And then, for example, I think it's inside the Sapphire contract, Sapphire Sol. Contract Sapphire Sol. Okay. So what can we do with it? Let's see. Suppose we want to implement the on-chain captcha. So there are some spammers, and the Rose token price is so low that it doesn't prevent spammers from spamming your contract. But what you can do is, well, you can do on-chain captcha because, as I mentioned, we have the random on-chain randomness support. So this is pretty awesome. But let's simplify captcha. So the only thing we want to do is, just add two numbers together, and if they match, then you're allowed to post the message. And if they don't match, well, you just, revert the transaction. So for this, we will use something called the captcha seed. And we'll combine this captcha seed, which is confidential, with the number of already submitted messages. So each message you post, there will be a new captcha generated for you, and you will need to, manually compute the result of that captcha and submit it along your message. Okay, let's see. So something like captcha seed, and then let's have a message counter as well. And then when you deploy the contract, you would want constructor. You would want to initialize this captcha seed. Oh, come on, VI. Captcha sit equals. Okay, and the Sapphire offers this random bytes precompile, which basically produces any number of bytes. I will use the 32 bytes here, and with no additional entropy provided, just an empty string in our case. And then when a user wants to set message, he first needs to receive the captcha question, the captcha riddle, and then submit the answer along the set message function. So to compute the captcha riddle, we will have this function, let's say compute captcha, the challenge. Okay, public view, and it will return two numbers, which you will need to add. Okay. So the first one is, let's say, something like this, A and B numbers. And then we will have something like a big chunk of this, which will then, hash and obtain the actual numbers ranging from, I don't know, 0 to 100 or something like that. So we will have for the entropy, we will use our captcha seed. We will use our message counter. Okay, and we will use something more unique because this is the same inside the same call. A0, B is 1. And now we get a bunch of random bytes here. And we just need to transform it to our unsigned integer inside some range, right? So something like this. Okay, what's the parenthesis? Yes. Okay, so this computes the captcha. And now in the set message, we want the correct answer to be provided. So we want to have something like captcha. And then what's the code for this? I would say, so you first want to compute captcha, use the same logic you used for the generation of the captcha. And then if A plus B equals captcha, then this is fine, right? So if this doesn't hold, then we will revert, right, with some message. I don't know, wrong captcha. Okay. Cool. So this is the captcha check. And then one more thing, we have this message counter here. So we will need to, if we set the message, we need to also increase the counter. So message counter plus plus. Whew, hope this works. Let's try to deploy it. We use the same testnet with the same key. Wow, okay, it actually works. Now the problem is that if I try to call the set message with this set message, I have a problem because I don't have the hardhead task to provide the captcha yet. Yeah, okay, let's add this captcha support to our set message as well. So the only thing here is we have the address, the message, and then we also have this captcha. And we just, add it as a parameter. Okay. So set message, args message, args captcha. This is fine, but we also need a task for obtaining the captcha, right? I think I have it here somewhere. So let's not lose time. So basically, the captcha task will just connect to our contract, and it will call this compute captcha and print it on screen. So if I just do not the set message, but captcha task. Oh, the address, sorry. The address is this one. Okay, so the captcha question is 93 plus 43. This is 136. So if I call set message, and if I type in 136, it should work-ish. Okay, it seems it works, but let's check if the message was really stored. So just call message. The message is confidential hello world. Yay, it works. So this is, for example, this is a very nice example how you can use the on-chain random number generator, for solving the captcha problem on-chain without using any intermediaries or bridges or web to servers whatsoever. Okay. Right, so this concludes our hands-on. I would just take 5 more minutes, and maybe if there are any questions. Otherwise, I would like to give you some more ideas where to look for afterwards. Hi, Mike. Okay, let's move on. So we looked at the. Okay, yeah. So it seems to be some bug in the demo star. Maybe you can check out previous commit from the demo star project, and maybe it should be just recently added this bug. Otherwise, I mean, I was testing the front end just half an hour before we started, and it worked. So probably some recent commit regression. Okay, so we talked about the on-chain, all the errors, all the possibilities we can have if we have a confidential contract. So one is definitely the shared secret I talked about previously. So the end-to-end encryption is just not doesn't only mean that it happens transparently between your computer and your smart contract, but you can also deliberately have part of the key stored on your device and the other part of the key stored on chain, and then when you combine the two, you get the data. So this on-chain encryption primitives are supported inside the Sapphire precompiles, and you can do, for example, the X25519 we use already in number of examples. They're really strong. For example, the emitted events are non-encrypted by default on Sapphire. You need to encrypt it by yourself. So using this mechanism can be useful. You can also have something like, I know, your local shop dealer gives you a part of the coupon, and then you combine that chunk of the coupon with the secret stored on chain, and then you get some bonus or some reward for this, for example. Okay, we also support the SECP256 generation on chain. So why is this important? You can basically generate a whole transaction on chain and also sign it, and then return the signed transaction, which was generated on chain, back to the user, and then the user broadcasts it. And if you follow the crypto world, the buzzword of 2023 and maybe probably 2024 also is the account abstraction mechanism in the Ethereum world. So the mechanism that allows the smart contracts to create to have some kind of a balance and then sign transactions on behalf of someone else. And this is supported in Sapphire out of the box because the state is confidential, right? And you can store the private key on chain and just generate and sign transaction on the way. And what you get with this is, for example, the gasless transactions. You don't need any third party. For example, the OpenGSN is known bridge, which is the gas gas station. If you don't have a gas to pay for the fee, you then submit your transaction to your GSN relayer, and it pays the fee on your behalf and submits your transaction. But here you don't need this because you can ask from the contract directly to sign the transaction, and the contract trader can have some tokens there for the gas fee, for example, and you can submit. You sign the transaction yourself. You send it to the smart contract using the view call, which is free anyway. The view call then generates the wrapper transaction, which pays for the fee. It gives it back to you, and then you submit it and broadcast it to the network. Comparing to the GSN relayers, where there can be censorship, here you can just communicate directly with the blockchain and submit the transaction. So you get rid of any bridges, any relayers in between. And using the same concepts, you can also bridge other networks. For example, you could have a light client for Bitcoin, and you can connect to the Bitcoin directly without using any. You need an oracle if you want to have prices for DeFi and so on, but you don't need any layers. You can just run the light client inside your browser, and then you get if you have a transaction on Bitcoin network, you generate a proof for that transaction and submit the proof directly to the chain. And then inside the chain, it can verify and if your transaction is real, and it can then, for example, mint some on-chain tokens for the wrapped Bitcoin on Sapphire, for example, or stuff like that. Another use case, single sign-on. So you can store your credentials. Not your credentials, some proof that it's you on chain, and then services, for example, your mail provider or your GitHub provider can communicate with the contract on chain, and you get using the view call without paying for any fee. You get the receipt that it's really you that you can use the service, and then you hand over the receipt to your service. And the service can check whether the receipt is really valid, right? And you can use on-chain services. Again, this is just because we have the confidential contract storage. You cannot do that in plain Ethereum. So this is also the demo here. You can already play with. It integrates the WebWav, and you can use it to log in to any service. You can implement a service which uses this for login. Okay, next, the gasless contracts I talked about. This is also called the autonomous contracts, because the contract can generate the transactions and you can then broadcast it. But this EIP 155 standard defines how the transaction looks like, and we also have the support for this in our Sapphire Precompiles library. And you can use it to generate transactions and sign it on chain. So how this works, this is the diagram I talked about. So the signed transaction is returned back to you, and you can then broadcast it yourself without using any layers. And I'm just, I'm not talking blindly. This is actually already implemented and it works. If you go to Playground Oasis.io demo voting, you can actually try out demo voting. Yeah, the interface is pretty similar. it wants to connect to the testnet probably. Yeah. Yeah. Okay. Okay. So here's the poll, and you can submit your vote on chain without using any tokens to pay the fee, because the one who deployed the poll contract, me probably, deposited some tokens, some test tokens to pay for the fee for anyone who decides to vote. So if I took, so yeah, do you like the Sapphire 101 workshop? Yeah, okay, I fall asleep, almost. Didn't have coffee, okay. And I just sign the call. I don't pay for any tokens. I don't pay for any fees myself. Maybe I can just, look at the balance, and the balance will not change. And now the vote is submitted, and it will be unwrapped on chain and then computed, and the number of votes will be counted, and yeah. So I submitted my vote, and I did not pay for any fee. Okay. So this is pretty awesome, and this is not using any GSN layers. It just communicates directly with your client and the chain. This is a playground.oasis.io/demo. I think you can try it out, and there's also source code available if you wanna check it out, how it's implemented. Okay, another hot topic is the Oasis privacy layer. So we offer a solution which connects to a number of other networks, Ethereum, Binance Chain, Polygon, and so on. And the idea is, if you already have a dApp deployed on that chain, you can also use parts of your dApp for confidentiality and use Sapphire in this regard. And you need somehow, you need a bridge to communicate between the target chain and your home chain. We use Seller IAM for this. And in this case, the Sapphire computes the confidential part, and the other chain then takes over and produces the result. Okay, last but not least, playground.oasis.io. So we collected a number of demos, examples, and everything interested. If you're interested in on this website, and if you also have a dApp you like and you made it on your own, you can submit the PR, and we'll add it to this list. This is one thing. I would really encourage you to run a client node, Sapphire client node, for example. So you will not need any third parties for your dApps. And finally, check out our documentation. I think it's really nice, treasury of recipes, how to build on Oasis, how to get involved into running nodes, writing dApps, thinking about the confidentiality, writing security, secure applications, and so on. Right? Okay, so this is from me, and I would kindly thank you for your cooperation. Any questions, proposals? And I can export the slides finally. a second. How do I export? Okay, let me see if I can share the slides with you now. Where is it? Here it is. Okay, share. Crap. I think I won't be able to share. Yeah. Okay, let me upload this to my private server. Stupid Google. It's here. Here it is. Okay, now hopefully. Okay, here they are. So you can access the slides here. Andrew, regarding your question, yes, you are right, but the communication is not done directly. It's done via the seller bridge, and the seller runs, relayers, and then it monitors the transactions on Sapphire. And when something happens on Sapphire, the seller relayers then wake up and transmit that transaction to the target chain. Okay, so let's conclude our workshop. Thanks for your time, and I hope to see you soon on Discord channels, and let's start building.